Now, if you had a chance to complete the rest of the table, I want you to compare your results with the ones that are shown on the screen. So we had all of these heights calculated, and we used those values as well as the radius to calculate each of the volumes. Now, what you should have noticed is the case where you had a radius of 5 centimeters and a diameter of 10, gives a height of 10.92 centimeters, and gave a volume of 857.22 centimeters cubed, which was the largest of the volume values in this column. So we noted that the largest volume occurred when the radius was 5 centimeters and the height was 10.92 centimeters. Therefore, it appears that the maximum volume is achieved when the height was approximately twice the radius. You can see that this value is just about twice the value of the radius. Here's the table or portion of the table that we were looking at, had a radius of 5 or a diameter of 10, and the height was 10.92 centimeters, which was pretty close to twice the radius. So we're going to say that the optimal dimensions occur when the height is twice the radius or when the height is the diameter, the same value as the diameter, since the diameter, of course, is twice the radius. Now, when we look at our formula for surface area, and we have 2 pi r squared plus 2 pi r h, but we know that the optimal dimension is going to be when the height is twice the radius, we can sub that value of h into our formula. So we're going to replace h with 2r, since our height is going to be twice the value of the radius. And when you simplify this expression, you can see that 2 pi r squared is unchanged at this point. But this part, you have 2 pi r times 2r. 2 times 2 is 4, and you've got your r times your r, which is r squared. So you have 2 pi r squared plus 4 pi r squared. And if you add those two together, it gives you 6 pi r squared. Therefore, we can conclude that the optimal surface area of a cylinder is given by the formula surface area equals 6 pi r squared, and it happens when the height is twice the radius.